For the first year of the Pacific War, Allied pilots reported fighting a machine defying physics. It could streak past their sights and turn at angles that conventional aircraft simply could not follow. Claire Chennault and other intelligence officers filed reports on this new Japanese fighter before Pearl Harbor, but United States Command largely ignored them. Based on known aeronautical engineering limits, they assumed the flight data was mathematically impossible. On this map, the 1937 Japanese Navy specifications demanded a fighter that could launch from remote land bases, escort bombers across vast stretches of the Pacific, and still have the speed and turning radius to win a dogfight when it arrived. To achieve that, Chief Designer Jiro Horikoshi faced massive material constraints. Japan lacked high-tensile steel alloys, meaning he had to rely on the Nakajima Sakae, a relatively small radial aircraft engine putting out just 950 horsepower. To bridge the gap between that low-power engine and the Navy's extreme performance targets, Horikoshi's team turned to a design philosophy stripping the aircraft of every possible gram of weight. He initiated radical weight-saving measures, constructing the airframe from a novel alloy called super ultra duralumin. It was incredibly light and strong, but highly brittle. Looking at this wireframe, you see where the weight was shed. Horikoshi eliminated heavy steel armor, housing massive fuel tanks directly inside the unified wing without self-sealing rubber. This exceptionally low wing loading allowed the Zero to carve tighter turning circles than heavier conventional fighters. But stripping defensive features created a lethal vulnerability. A single tracer round piercing that ultra-duralumin wing could easily rupture the unsealed tank and violently ignite the entire aircraft. The Zero achieved absolute aerodynamic supremacy, but it relied on a foundation of extreme structural fragility. It was a perfectly designed glass cannon. In June 1942, a Japanese pilot taking part in the Aleutian campaign took a hit to his fuel line and executed an emergency landing on the island of Akutan. He flipped the aircraft in a marsh, leaving the fighter remarkably intact. U.S. forces recovered the plane and repaired it, repainting it with American test markings to exhaustively test its capabilities in the air. Flight testing revealed major flaws. At speeds over 260 miles per hour, the light aircraft lost aerodynamic stability, making high-speed dives uncontrollable. Furthermore, the massive propeller generated enormous torque that fought the ailerons, making the rightward roll rate incredibly sluggish. Armed with this data, American commanders issued immediate new tactics. If a Zero gets on your tail, execute a split S, a diving, sharp turn to the right, and the Japanese plane won't be able to follow. The Akutan discovery transformed the Zero from a supernatural terror into a predictable machine with fatal mathematical limits. As U.S. pilots refined their defensive maneuvers, Grumman was already preparing the hardware to exploit the Zero's structural limits, the F6F Hellcat. Instead of a 950 horsepower engine, the Hellcat housed a massive 2,000 horsepower ride radial. That sheer thrust allowed the U.S. to load the plane with thousands of pounds of heavy armor plating and still maintain high speeds. That thick steel plating was crucial. The Zero's primary weapons, its 20mm cannons, fired large shells, but with a notoriously low muzzle velocity and a slow rate of fire. The Hellcat's armor could reliably absorb those hits. American engineers didn't try to outturn the Japanese fighter. They leveraged raw industrial muscle to build a heavyweight brawler that shattered the Zero's delicate elegance. Over time, the Zero's lack of protection yielded a catastrophic secondary effect. Every time one caught fire, Japan lost a highly trained, elite veteran pilot who took years to replace. Desperate to compete with the Hellcat, Mitsubishi began developing a heavier, armored successor known as the A7M Reppu. However, lifting that additional armor required a 2,000 horsepower engine. Japan was largely cut off from high-tensile steel and alloying metals, making it impossible to manufacture those larger power plants at scale. A massive earthquake in late 1944, followed closely by relentless Allied bombing raids, leveled the Nakajima and Mitsubishi factories, permanently killing the A7M project. The Japanese Navy was trapped. They had to send green recruits in stagnant, fragile 1940s airframes up against thousands of heavily armored second-generation American fighters. By the final year of the war, these inexperienced pilots were being shot out of the sky in their obsolete Zeros. Realizing the planes could no longer survive standard aerial combat, Imperial Command made a desperate tactical shift. They stripped the aircraft of all remaining non-essentials to deploy them as manned, guided weapons. They loaded the Zeros with 550-pound bombs for one-way trips into American warships. It was the ultimate weight-saving measure, eliminating the need to carry fuel for a return flight. The extreme engineering compromise that made the Zero an apex predator in 1941 dictated its grim conclusion. Once the structural math was solved, the fighter's brilliant agility condemned it to serve as a desperate suicide weapon.